You've probably noticed that Chapter 7 is a lot about actually using the antiderivative for something, where up until now, in at least Chapter 6, we were just trying to take the antiderivatives. And so in 7.1, we basically were able to do velocity, position, and acceleration. That's kind of where we use the antiderivative. And here what we're going to do is actually find the area between two curves. The reason I have these three graphs there is basically, let's say that this graph right there, or something similar, we will call it f of x. And we'll say we're going to go from A to B. If I asked you to find the area underneath that curve, wouldn't you just integrate from A to B f of x? Isn't that what you would do? Right? And basically, if you look at it, you would be finding that area, correct? If you did that? Well, that's pretty simple. And what if I gave you something similar, but maybe this, we'll call it, for our purposes, and you know what, I'm going to use a different color so that when I go to the next one, I can do the same thing. Let's say this one looked like that, but we'll call that just something else, obviously, because it's not also f of x, it's something different. And we'll go from A to B again, so the same A and B. You know, it could be 1 and 2, or 4 and 5, or 1 and 5, who knows. But if I asked you to find the area there, you would just integrate g of x, right? Of course, dx on both of these, but in A to B. Dx basically means you're going to the x-axis. That's what that means. And if you did that one, you would be finding that answer, correct? Are we in agreement with those two statements? But this says area between two curves. So basically what we're going to do with that slightly bigger graph is we're going to put these two graphs together. And I just want to find the area in between them. It's not quite the average. In some cases it might be. But I think that's a pretty good representation of my f of x over there, don't you think? It's pretty close. I would be writing these down, yeah. And I can stop after this if you've kind of just been following along, that's fine. And then I think this is a pretty good representation of the g of x, and that's why I changed colors, so that you could see it on here. We'll say the same A and B. And what I'll probably do up here is I'll kind of draw in those areas again, and I'll do some erasing up here, so maybe just follow along at this point. Once again, if I just wanted the area underneath the red, you would just integrate it, and it would give you all of that, correct? If you just integrated the red one, it would give you all of that. Agreed? But do you also agree that if I integrated the green one, it would give me that? So if I just want the stuff that's in the middle, wouldn't I take that red shading and just subtract out the green shading, and wouldn't that leave me the stuff in the middle? And so that's exactly when you look down here, that's why there's a minus. Okay. So what some people have said in the past is take the top one minus the bottom one. Could you see why they would say that? Because this red one is on top and the green one's on the bottom. But what you might want to say is take the one that's furthest from the x-axis and subtract it from the one that's closer. Because if you actually do subtract it out, you're basically just taking all of this away, which leaves you with the stuff in between, which is exactly what we want. Okay? And so that's why this formula is right here. But do you notice that I have it in brackets, which means if you want to, if it's possible, you can do algebra in here first and then integrate. Save yourself a whole lot of time. But you better watch out with that negative, because sometimes with negatives you have to remember to distribute them. Okay? So watch out with that and be careful. All right? So any general questions? I think it'll probably be helpful when we actually look at an actual function and see what it looks like. Okay? So right here, determine the area of the region bounded by the graphs of y equals x squared plus 2, y equals x, x equals 0, x equals 1. Well, the good thing is I gave you things that we should have a pretty good idea of what these graphs look like. So y equals x squared plus 2. What's that going to be? Parabola that's been moved up 2, right, from your parent graphs in advanced math. So in general, we know if you put 0 in for this one right there, you get 0, comma 2. And if you put 1 in, you get 1, comma 3, right? And I think we could agree that that would just keep going like that, right? And doesn't it also technically go this way? It does, but I looked ahead and I only gave you the graph of what we needed. Okay. Y equals negative x. No, not y equals negative x. And do you have the newer graph compared to mine? Or do you have the older one? You have the older graph. Oh, that would explain why I made a new one. Y equals negative x. Well, what if you put 0 in there? And I better do a different color. So if you put 0 in there, it's 0 comma 0. What if you put, say, 1 in? And if you put negative 1 in, you get 1, right? So it's y equals negative x is that one, right? X equals 0 and x equals 1. What can you tell me about those? What does x equals 0 look like if you had to graph it? X equals 0. X equals 1. Does that enclose a shape? It says the area bounded, it's almost a trapezoid, except it's arced up here in the blue. I'm going to trace out what it creates. Do you agree it creates that? Okay. So to find the area between, which is this, what we're going to do is we're going to take the top one minus the bottom one. And it's actually going to work, and I'm going to see if you can explain why. So here we go. Integrate from A to B. Well, what are A and B in this problem? I'm going from where to where based on what we were given. 0 to 1. Very good. Which of the two, the blue or the green, is the one that's on top? The blue. Which one's the blue? X squared plus 2 or y equals negative x? Yeah, so okay, so, and I always put the brackets, you don't really have to do that, but x squared plus 2 minus, and then I like to put parentheses after I do the minus because of that distributing issue. Okay. A, and again, negative x. So this one was pretty simple, so you probably didn't really have to put the parentheses, but again, I like to be extra careful. Is there any simplifying I can do before we go and try and figure this out? So 0, 1. It becomes x squared plus x plus 2. Do you agree that's what we would get if we do simplifying? The question is what? Okay. Now, wait a minute. When we go to the TI-83 and graph x squared plus x plus 2, is that going to be the graph we see when we do that? We're not going to see that graph, are we? But I'm guaranteeing you that that graph from 0 to 1 will have the same area as the one I'm looking at right there. So can you use the TI-83 to do it? Yes, you can. Why don't you go ahead and do that right now and find the answer to that question. But again, when you graph it, you're not going to see this graph here, but you'll find an equivalent graph. Oh, hopefully that was enough time to put that in there. And again, this is one that we could have done by hand. That's what I was just saying during the break there. This would be x to the third over 3 plus x squared over 2 plus 2x, 0 to 1. You plug in 1, that's pretty simple, and you subtract what you get when you plug in 0. What's this actually called again, what I just did? Fundamental theorem of calculus. So it'd be 1/3 plus 1/2 plus 2 minus 0. And you get what? So 2 and 5/6. Or what, 17/6? How come that works on this particular case? The example I gave you back here, top minus bottom made sense because we were just erasing that stuff. Why does top minus bottom make sense? I didn't erase this stuff down here. Why does that make sense then? It still works. It's right. Yeah, so we're really subtracting a negative, which then turns it to a positive, so it adds the area to what we have. No, this is right on. This is right on. That right there would be a negative area, but we subtracted it. So we subtracted a negative, so it added it to my other area. I asked why it worked. Because here we were just subtracting out this area, which just made it go away. So why would subtracting still work? I didn't want to make this go away. I didn't want to make it erased. I wanted to add it on. And so that's what we really did. We subtracted the negative, so we added it on. That's why it worked.